Let's deep dive into the various components we'll be designing for our app. How will our web crawler work exactly? Suppose we have already fetched a list of URLs from the web that we haven't crawled yet. For each URL, web crawler will look up a map that tells if it has already crawled it or not. Here we can use the key as IP address of the URL since it is a universally unique key. If we find the IP address in the map, it means we're looking it up for the first time. So we need to find the IP from the DNS resolver and store it in the map. Once we've found it, we can establish a connection with it in order to reach the contents. In order to read the contents. Now, reading the contents for every URL every time a search is made is definitely not a scalable approach. So what we can do is to index this content in a distributed indexer uh, that we will be building later. In order to find more URLs to crawl, we can pass the current URL document to look for new URLs and add them to the unvisited URLs list. Then we can repeat all these steps for this new list of unvisited URLs. But now let's think how we can generate URLs that we can crawl after crawling the currently picked URL. For that, we need to think what kind of URLs we can have. One kind of URL is what we can call maybe a base URL. Let's suppose we have a URL like foo.com/a. From this URL, we can pass its document and find URLs like foo.com/a/b. And from that part, we can further find foo.com/a/b/c. So we can traverse the past URLs in either of the DFS or BFS phase. Another kind of URL we can get is what we would already be a multipath URL like foo.com/a/b/c. From this URL itself, we can generate what we can call path ascended URLs and put them in the unvisited bucket. These URLs here would be the parents of this URL, like foo.com/a/b and foo.com/a. To maintain the list of unvisited URLs, we will need a data structure to store them, and a queue might help us with it to process the URLs in FIFO manner. Since we could have a very big list, the queue will be a multi-server distributed queue. To optimize processing further, we could spawn multiple threads on each server to pass and index multiple documents parallelly. So each worker thread will be managing its own distinct subqueue. But how do we decide which URL will go to which subqueue? For this, we could define a hash function which will take care of this mapping. The other thing our algorithm needs is a DNS resolver which would map the hostname to IP address and cache it. When further URLs of the same domain need to be crawled, the crawler will look up this cache instead of resolving it again and hence reduce latency. If there's a cache miss, we'll resolve the domain from either of the local or global DNS. Now, while our crawler is looking for more URLs, it could be that multiple links go to the same document, and reprocessing the same documents would unnecessarily add weight to the crawler. So to prevent this, perhaps we could also design a URL dedupe service, whose job would be to find if a URL has already been crawled or not, and will help us in skipping its processing. Checksum is quite a common approach to achieve this. Is there any more content for which we can skip processing? What about adult content or child logged content? So let's say we have a dedicated URL filtering service that helps us with this. The blacklisting could be based on various things like domain name, prefix, or protocol type. So now moving to the part of actually processing the URLs, the first thing we would need is a service that will download the document of that URL. Let's call this service document fetcher service. Since we're only supporting HTTP for now, this service needs to be extensible for other protocols in the future as well. A document could be a really big file, so is there a way to efficiently process each document? What if we could divide the document into smaller documents and process each of them separately? Perhaps we could have a dedicated document streaming service which would do this. To optimize storage and increase performance, we could perhaps cache a very small document in memory itself for quick lookup and large documents onto a file storage. This service can be used by other services as well to read the documents to process further. Now, just like we did for URLs, could we be getting the same document to process multiple times? What if the same document is there under different URLs or the same document is on multiple servers? To find this, we could have a document dedupe service which would find these duplicates using the checksum approach. Now, once we have received a distinct document and batched it into stream, each stream can be processed via a service, say document indexer, which would index each word of the stream for faster search results. We need this indexer so that every search query that users hit don't need to crawl the doc again. Since this entire process is quite heavy, it will be done behind the scenes with a scheduler, like maybe once every day. So while we won't have strict consistency at a given time, we will be aiming for eventual consistency over a period of time. Finally, what we need is to extract next set of URLs to be crawled. So for this, we can have another dedicated service called URL extractor, which would pass each stream to extract more URL links, and these will be included in the URL queue. Now, since we're done with the high-level components of the web crawler, let's think around the type ahead suggestion service. Again, if we're processing every time a user queries Google, that could be really inefficient. So instead, we could use a pre-processing architecture to pre-store all the possible search strings in a data structure. Now, when the user is typing a query, we'll search all the strings that are prefixed with that query. What data structure can be used to support this? We could use a try structure since it's well known to be used in applications which require string search. Since we also need a minimum latency type ahead, we'll combine try with in-memory indexing as well to be really efficient. A basic try is built with each letter of a word at each level. For example, if the word is caption, each letter will be the child of the previous letter. Since this will be a lot of words for the scale of Google, can we optimize it in some way? Well, we could club some of the most widely used letters together like iron, a, in, ital, etc. This would reduce the number of nodes we need to traverse while user queries the engine, therefore reducing latency to an extent. At this point, you can brainstorm any questions that might help the interviewer understand your approach better. Like, let's say we want to display top 10 suggestions when user enters a query. How can we do that? We could perhaps have a count of number of searches that end at a particular character in the node itself. For example, if a word captain is being searched, its last letter N will contain the number of times that the word captain was searched. So now given a try where all leaf nodes contain the count of their queries, we can traverse the subtrees till we find 10 nodes with most searches. Since we're traversing the subtrees, it would take more time to search if such queries are longer than 10 words. So is there anything we can do to improve the traversal? What if instead of traversing subtrees every time to find top 10 suggestions, we simply store it at each node? We'll need extra storage for this, but this will really help us minimize the latency, so that's fine. Now we don't really need to store the entire searches at each node and can simply store references to other nodes which will help us build those entire strings. This will help us optimize storage as well. We can throw in some more questions around try. To update the try, we can schedule offline jobs at some interval, like maybe every 5 seconds. A lot of searches may not even need to be indexed, so we could use a spam filtering layer before updating the try. It's also very important for a software engineer to handle system failures. So how do we recover the try from a failure? We could configure our try servers using master worker replica architecture. Master server will be used to update the try and workers to read the try data. Now, if a master goes down, one of the workers will take its place. At this point, we could use consistent hashing to redistribute the load among the new set of servers. But what if instead of one master node, all the nodes go down simultaneously? We would need a way to rebuild our try from scratch. To do that, we would need to persist the try data in a file periodically. To build a try, we could store its in-order plus level order traversals, since these two traversals are sufficient to rebuild a tree from scratch. To optimize searching itself, we could leverage caching the servers and even serving content with CDN to reduce latency.